Good morning, statisticians. This is Dr. Schulman. We've made it to normal distributions. I know, exciting stuff. Um, Obviously, like this and like the last chapter, they can get kind of tricky, especially this information. So I'm going to give you a little just breakdown of what the normal distribution is. The questions, I haven't looked at them yet. I try to see them as if it was you to try to like just get in your mindset if I'm seeing them for the first time. That's what I do for every video. So I'm sure the questions will probably have stuff about like subtracting stuff from means, figuring out how many standard deviations away, what the normal distribution is. So I'll start there, look at the chapter, and then do the questions for you. So I'm going to share my screen. Here we go. I'm going to move this. Hopefully it doesn't get in my way this time. So again, in case you're sure where we are, these are the modules for everything. I've done videos for everything that is due. Notice that there's a bunch of stuff here that it's grayed out that you don't have to do. Um, so we're up to this chapter, normal distributions. There's videos for everything up before this. We're starting with 6.1. And if you want to watch the videos, I'm sure these videos are pretty good and I'm sure they're fine. But just in case you want to have some more information, I just think that they're a little old and outdated. That's why I'm making them for each of them. So we got these problems to try. There's a lot of them. So this is the problems I'm doing. I'm also going to be looking at the book. So I might as well just have the book ready for us. So to get to the book, you go to My Math Lab. You go to Open My Math Lab. And a lot of people have been reaching out to me for Zooms, which is totally cool. I also pushed back the dates for a lot of stuff because some people didn't finish. See, now chapter 1 and 2 reviews are due on the 17th. Why'd I push it back a week? People couldn't get it in. Some new people joined the class. And guess what? I was fine with it. So if you're struggling, just reach out. So we're in My Math Lab. I'm gonna go to eText Contents, and I'm gonna click Pearson eText, and that'll open up the book. I'm gonna go to chapter 6. Before just showing you everything that we have. Chapter 6 is gonna not be too hard, I hope, but we'll find out together. Obviously we'll find out together. This is what we have. Now, I'm going to give you just like a little bit of basic information. How do we get here? You go to My SFCC, Microsoft 365. This is your notes, intro to stats, 6.1. Look at all the ones we've done already. Exciting, exciting, exciting stuff. So what is a normal distribution, right? What's a normal distribution? It's just a bell curve. Don't let anything freak you out about it. And I know I've done this a couple times. I want to do it again. So let's say the mean for everybody. So not X bar. This is the mean for the population is 100. And we know it's going to be the standard deviation for this. And they like doing, was it big S? I forget the specific letters that they want. Sometimes some forgetful person. Let's say our standard deviation for the population is 10. This means this is 100. This is 110. This is 90. This means that being a -1 standard deviation away. Oh, sorry, this is what they're like. Sorry, that looks more like a music note. There we go. And +1 standard deviation away falls between 90 and 110. This should be 68% of all scores. Now, what does that really mean, right? What does that really mean? Do they have the percentages? They just have you doing Z-scores? I assume there'd be a picture somewhere. critical value. That's it. Okay. Wow. Okay. Well, they don't give you a lot, but that's okay. I'll just pull up a regular picture of a normal distribution curve. I'm gonna click images because that's what I need. It is 68. I just like to double check that I'm right. The next one's 95. The next one's 99.73. We're almost. So this means that 68% of all scores fall between this. We go another standard deviation away, right? Now if we're at plus 2 standard deviations or minus 2 standard deviations. So now we're at like 80 or 120. This means between these two values, guess what? We got 95% of our scores fall between them. And if we get, and remember, this just means that right here, right? About the rule of thumb, this is what's normal, right? This is like what should happen. Now, once you're more than 2 standard deviations away, so if we're between 130 and 70, this is going to be 99% of our scores. That's what this whole thing means. So this is kind of the curve that they're talking about when they're talking about the normal distribution. What is this like? This is like heights for people. I did intelligence about everybody's weights, right? You're going to have some people who weigh a ton, some people who barely weigh anything, but most of us are going to fall in the middle. If we get the whole population, we should get this curve for most things like, I don't know, height, weight, um, intelligence. Like just think about like basic characteristics of people or things. Um, they should all fall like this in this beautiful normal distribution. So that's pretty much what it is and where it comes from. Let's look at the book and see what it has in store for us. It's a bell-shaped graph when this is when the mean is 0, is standard deviation 0, and this is when the standard deviation is 1. This normal has a distribution of standard deviation of 1. So in this section, we'll present the standard normal distribution, which is specific normal having these 3 options. Okay, so this is like a specific, this is like the standard one, the one that they all should be based on. So where this is not an example, right? Normally the mean would be like 5 feet tall, sorry, 5.5 feet tall for women, or 100 or 100 for intelligence, something like that. But this is for like kind of like everybody. Okay, hopefully that's clear. All right, and now we have normal distributions. If a continuous random variable has a distribution with a graph can be described as an equation in 6-1, we say it's normal. So it's got to be bell-shaped and symmetric. The bell shape just means there's a bump in it, and symmetric just means whatever's low matches the high. Both sides are the same. It's not left skewed, it's not right skewed. It is normal, just like that. I'll keep on going. All right, so here's the formula. Now, fortunately, we won't actually use the formula. What? Why not? All right, well, they don't want us to use this formula. They made it extra small for some reason. I might as well tell you what all the parts are since they're hiding this from you. We have 2 constants here. We have 2 constants here. So what do all these parts mean? I hate when they just are like, this is too hard for you, you know? So I might as well show you what they're talking about and what this formula is. And then we're going to graph the formula so you'll see I'm not a big liar. So Y is the output. It's always our output. It's going to be our either our predicted value or what comes on the y-axis. That's that sure output variable. That's all this one is. E, this is actually the money constant. We use it for a ton of stuff. It was made by this guy named Euler. We're going to use them. We might as well see, look at that funny hat from this Danish guy. So why did Euler come up with the constant? Dun, 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 dun. It doesn't say. We use it all the time in money. I'll show you how I use it. Maybe it's in his Wikipedia. You never know. I kind of forgot where it came from. I knew he was really into astronomy. He worked with gas. He popularized pi. He has this, which is the imaginary number. Cool. He gave the current definition of E, the constant logarithm, and it's the inverse of the natural log. That's what it is. Um, they don't really show exactly everything, but that's okay. Here we go. All these formulas are pretty cool. Just doesn't say why he came up with it, but obviously he's a lot smarter than I am. I can just show you what it's used for. I guess I can't tell you why he came up with it, but that's okay. I might as well show you what it's useful for. So the first part is E. Now, what is this crazy E? E equals 2.718. Why do we use it, call it like the money constant? Because like if you want to just do general interest of something, let's say the sales tax is like, or I want to leave a tip of 20%, right? So we do interest equals principal times rate times time. This is simple interest. It's not usually used how it works, but our interest is our principal. Let's say our bill was $50 and we want to leave 20%, right? We just want to do it one time. Okay, so interest is 50 times 0.20. And we're just doing this after 1 year or like one time of actually going out to eat. So 50 times 0.2. We know our interest is $10. So this means the total's like kind of like the tip. So it's the 50 plus the 10, which is $60. Okay. However, real numbers don't work like that. So usually it's the amount equals this is what the amount equals. Principal 1 plus r over n to the nt. Now this is compound interest. So let's say this is going to compound time after time after time. This is how like CDs work. This is how your money makes money for you. A is the amount. P is your principal. So I still start with $50. 1 plus the 20%. And let's say it compounds every month. So that's 12. And we do it for 2 years. This is your rate. This is the number. That's the time. So what do we have here? Well, 1 plus 0.2 divided by 12. So 0.2 divided by 12 is 0.016. We add the 1 to it. I'm going to take this number and I'm going to raise this to the power because 12 times 2 is 24. Then all I have to do is multiply it by 50. Oops. Multiply it by 50. And we have a total of $74.35. So what does this mean? I made 24 bucks, right? So this is if I have $50 at a 20% interest and it gets compounded monthly. This means every month it happens. How much money will I have in 2 years? I'll have $74.35. However, things can come down daily, monthly, quarterly, weekly. You can like set this compound to be whatever, but Euler is this one. And this one means continuously compounding. It's used a lot of times for half-lives, which is cool. It used a lot of times for this is what would happen if it was compounded by every second. That's what this value comes in. So your amount is your principal 50 times 2.718. It's like the money pie. And we're raising it to the 0.2 we're raising it to the rate times the amount of years, which is times 2. And this would be if it was compounded every second. E is just the inverse of what is called a natural log, or ln, and it has a little graph. So that's what this number is. That's what the E stands for. Now the E is always being raised to something, so it's raised to the negative 1/2. This is your input, minus the mean, whatever our mean is, divided by the standard deviation squared. So all of this whole thing, I'll put brackets around it, this whole thing, and this parentheses got to go a little lower. This whole thing, the E is being raised to. Now we're dividing it by the standard deviation, the square root of 2 times pi. Now, I'm sure everybody's heard of pi. Pi is like the circle constant. The circumference equals 2 times 3.14. Sorry, the circumference is the diameter times 3.14, and the area is pi r squared. And the circumference could be always called 2 pi r. Now, the problem really with pi, there's a reason why there's a 2 here. There's a reason why there's a 2 here. Just like with the circumference for 2. Basically, if I have a circle is basically every dot taken from the radius. So it's like an equidistant amount of points from what's called a radius. I know, exciting, right? But we don't use the diameter. So instead of using 2 times pi, a lot of times, and we know pi is 3.14, a lot of times we're going to use what's called tau, and tau is 6.28. Tau uses the radius and not the diameter. So this would just be the square root of tau. In most formulas in math, it's 2 times the pi. The only one that isn't is the area formula. This is the only formula where pi is better than tau, and I think that's why they teach people pi's instead of tau's when they were little. However, as soon as you go like past just area, like wherever all the math kind of comes together, we use this tau formula. That was a lot. So this is some crazy formula, right? And this gives you how we get the normal distribution. And they're telling us that our mean is 0, right? I'm pretty sure that was it. The rules for the standard one. They say the mean is 0 and the standard deviation is 1. All right, so our mean here is going to be 0. And our standard deviation is going to be 1. Over the square root of 2 times pi, or tau, if you'd like it. You know, it's up to you. So I'm going to just see what this looks like. E to the negative 1/2 x minus 0 squared over 1 over the standard deviation of 2 times pi. So ready? So y equals 2.718 to the negative 1/2. This is just going to be x minus 0 over 1, so it's just x squared. Sorry, that's not where the line goes. And this whole thing is going to be over the square root of 2 pi. So let's draw it for the standard one and see how it looks. So usually I just do this in Desmos. But you can do wherever you want. Do you need y equals? Nope, but I might as well have it. So we have y equals. Is there a little e? There should be. Yeah, it says exponent. Here's e. If I just leave it as e, it already says it's the 2.718. There's the line. Then I have to raise this to the negative 0.5, which is 1/2. Parentheses. x. All I have to do is what? Square this thing. Okay, it already looks almost exactly like the picture. And now I have to put parentheses around the whole thing. Well, not around the y. So that's the top. And I'm going to divide this by the bottom. We know this is just 1, remember? So it's just the square root of 2 times pi. Is there a little pi guy for us? Here's our pi. Here's our e. Here's our natural log. So there's our 2. Oh, sorry. That's not our pi. That's another function. Here's the NPR NCR for number theory. Just going to extend this. Do they give us a pi? That's okay. If I write the word pi, maybe it automatically will come up. Oops. There it is. I just typed in pi and it turns into a pi. And here we go. So there's the top. The mean is 0. This is the exact graph they want. And it goes down here and it's getting really close, but it's not touching. But this is the graph they want you to make for the specific one that they have. Remember, this was going to be x minus 0 over 1, which just turns into x. Anything minus 0 is 0, anything divided by 1 is itself. That's why it's just an x squared. It's a negative in the front over 1 times 2 pi. And it should look like the picture. Ta-da! I did it for this one, which is the normal Bell shape. And that's what we have right here. There we go. I know it's not the prettiest thing in the world, but that's its y-intercept, and these are its pieces. Cool. So use the formula. At least we know what the formula is and where it comes from and the pieces of it. It says we don't have to worry about it, which is fine. Fortunately, we don't actually use it, which is a shame. There's your E value. There's your mean and standard deviation. So the major focus of this chapter is normal probability and probability distribution, but we begin with a uniform distribution, so we can see the following 2 properties. The area under the graph of a continuous probability is equal to 1. There's a correspondence between the area and the probability, so probabilities can be found by identifying the corresponding areas of the graph. Okay, so they're telling you area is height times width, which is fine for area, right? Height times width. Basically, the best way to think about area is always whatever your base is. In this case, they're using width for the base times the height. If you use this formula, I promise it's going to work no matter what the shape is. As long as you take whatever the base is and times it by the height of that base, you will always get it. You can, if it's 3D shape, take the area of the base and times it by the height, you will always get it. Okay, so just keep that in mind. All right, let's keep going. Dun, 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 dun. A continuous random variable has a uniform distribution. Its values are equally spread over all the possible values. The graph of a uniform distribution results in a rectangular shape. Okay. Now we have a density curve. The density curve is the graph of any continuously probability distribution, and any density curve must satisfy the requirement that the total area under the curve is exactly 1. Okay, which makes sense because if we really look at our picture, all the area under the curve, we add it all up, we get about 99%. So the area under this whole thing's got to be 1, which makes sense. As long as it's continuous, the area under the curve must equal 1 because that's the probability of everything coming out of it. Because the total area under any density curve is equal to 1, there's a correspondence between area and probability. Ta-da! All right, we get to try one. So during certain times, oh, and this is John F. Kennedy Airport in New York City. I hate when they use acronyms without saying where it comes from. The passengers arriving at the checkpoint have waiting times that are uniformly distributed between 0 and 5. Now, what does this mean? See how this business isn't curved, right? Isn't that it's like rolling a dice. Remember we're talking about uniform before we got the normal and we got uniform. This is like no matter what, if I roll a dice, here's my beautiful dice. Sorry about that. My phone keeps getting text messages and I don't know why. All right. So ours is going to be 0.17. All of them are going to be 0.17 or 0.16 something, something, something. Because no matter if I roll a 1, I have a 1 out of 6 shot. And 1 divided by 6 and 1 divided by 6 is just going to be 1 divided by 6 is going to be 16.7%. If I roll a 2, so this is still 1 out of 6. A 2 is 1 out of 6. A 3 is 1 out of 6. A 4 is 1 out of 6. A 5 is 1 out of 6. And a 6 is 1 out of 6. So all of these are going to be exactly the same, no matter what they are. Now, if we add them all up, 1 plus 1 plus 1 plus 1, 1, 2, 3, 4, 5, 6, we get the 100%, right? So that's what they're trying to show you with this uniform distribution. 1 divided by 6 is this 16.6, or I just rounded it to be 17% because I don't like the little bits that we're missing. Now, if we add this, 2.17 plus 0.17, that's the third one, plus 0.17, that's the fourth one, plus 0.17, sorry, plus 0.17, plus, and this is the last one. You can see that we're just about at 1 without the rounding error. This is what they mean by uniform distribution. And so there's just 20% a chance already. 0.20, 20, 40, 60, 80, 100. Ta-da! So this means everybody has an equal shot between waiting 0 and 5 minutes. It's always 20%. It could be any value. So it's possible to have a waiting time of 1.234567 minutes right here, but it's still a 20% shot. That's what this means. Cool. Waiting times for airport security. Okay, so given that the uniform distribution is in 6-2, what is the probability that a randomly selected passenger has a waiting time of at least 2 minutes? So at least 2 minutes. So that's 2 minutes, 3 minutes, 4 minutes, or 5 minutes. So look, 1, 2, 3. See how you just got to go across. You might, but it's not. It's 3. It's 1, 2, 3 across, and they're all 0.2. So that's a 60% shot. I know, exciting, right? It's height times width, 60%. Ta-da. So all of these things pretty much make sense. And we should be good to go. All right, so the density curve of a uniform distribution has a horizontal straight line. Does not have the curve, right? No curve here. Because the density curve of a normal distribution has a more complicated bell shape, it's more difficult to find the areas. Yeah. There's a correspondence between area and probability. So in 6-4, we use what's called the z-score. We found this formula before. If you forgot, that's okay. We all make mistakes. Just look back at it, Everybody's forgetful. Z-scores and all of them. So here's our standard distribution. That's what we have before. The population parameter has a mean of 0. We got standard deviations of 1. And total area under the density curve is equal to 1. Ta-da, should be equal to 1, more 99%. So here we go. It's not easy to manually find the areas. We can use technology. We can use appendix A-2. Because calculators give more accurate results, we strongly recommend using technology. Okay, so I guess they don't want us to use the table. And they don't want us to do it by hand. So they want us to use technology. I'm going to try my best to do this without technology. If they don't give us the formula, I'm not going to show you the formula because I guess they hate it. I've always, in the past, whenever I've learned this, I've always used the tables, but I'm not going to question the book. So we can do the cumulative area from the left. This is everything below the region. We got the area between two boundaries. All right, so these are the ones that I guess we can do. So based on the picture, whatever our score is, our critical value can be below or above. Remember, if you're past it, that means we are no longer regular or extreme. This means that our means are different. We can reject the null hypothesis and we are good to go. So standard normal distribution, A-2 is on 2 pages with negative and right. When working with the graph, avoid confusion between z-scores and areas. The distance along the horizontal scale and the normal one, refer to the leftmost column in the top row. And the region under the curve is the body. The part of the z-score denoting the hundredths across is A-2. Okay, let's at least find this table A-2. Then we'll go back. Let's see what they give us. I'm sure it's going to look exactly like everyone I've done before. All right, maybe it's in here. All right, well, we'll go to what we need to. Round z-scores to 2 decimal places. Yeah, okay. So we know what we have to do. All right. A bone mineral density can be helpful in identifying the presence of susceptibility to osteoporosis. Measured in z-scores, the population of z-scores are normally distributed with 0 and 1. Finding the area to the left of the z-score, 1.27. All right, so probability is everything less than that. And that's a shaded area. So we need to find the area in 6-5. So if we have a z-score of this, what's below it? If using table A-2, okay, where's this table? Is it in here? It gives us a piece of the table, but not the whole thing. So we look on the left side, it's 1-2. We go all the way to the right, but where does this 0.07 come from? I think that's the important part. How do we get the 0.07? Where does that come from? Using table H-2 by locating 1.2 in the left column. Oh, okay, I see what they mean. Okay, so to get this is the first part. If we have 1.27, this is just the beginning of it, and this is the end of the z. So 1.27, they give us at 0.8990. So this is everything below. I'm sure we can do this on like StatCrunch or something. So I might as well pull up the StatCrunch and see. I'm sure there's a little computer program for our StatCrunch that can do this for us. Oops, we don't need a data set. Let's see if we can open this. Sorry for all the tabs. All right. Here's StatCrunch. I bet it's I don't know. It's probably like a calculator or something. Calculator. We want a normal distribution. I like it. Okay, here we go. So let's see if we can use this crazy picture. Now we have a mean of 0. Cool, mean of 0. What's our standard deviation? Okay, standard deviation is 1. Okay, those are both there. We want everything below 0.8980. Okay. 0.8980. Compute. Sweet. Is this what they got? 0.815. They got 0.8980. Oh, sorry. They wanted less than 1.27. My bad. 0.897, blah, 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 0.898, 3 decimal places, 0.898. This means the probability of us having a bone density of 1.27 means that how many people have that? It's about 90% of people have bone density of 1.27 or less. That's exactly what this means. All right, let's see if we can find to the right. I'm assuming to find to the right, all we have to do is switch this and do it to the right. So let's say if we want everybody bone density has a bone density more than 1.27, it's going to just be 10% of the population. That's what that means. All right, so now it's bone density of -1. I don't know how you have a bone density of -1, but I'm not going to argue with it. And this is how you get the 0.84. So the probability with a bone density above -1 is 0.841, 0.841. And now between two, so everybody has bone density between -1 and -2.5. I guess I can click between. Sweet. So we have between well, this is the lower one, so this one has to come first. You have to do it in less than to greater than order, otherwise you're not going to get a real answer. See, this is a smaller number, that's why this has to come first. And there we go. So that's -1, and that's 2.5, and then they subtracted it, or you just use the program. Nothing too crazy about that. The areas can be found by finding the difference between the two areas found in the table. Not quite sure where that table is, but I think we're good to go. Don't try to memorize a rule, formula, focus on by using a graph. Okay, I like making the graphs. A and B, greater than A, less than A. Okay, that's fine. Now, I'm assuming we want to go backwards here. Usually they make us do backwards stuff for everything in math. Finding a z-score from a known area. Draw a bell-shaped curve and identify the region under the curve as it corresponds to the probability. Use technology or table A2. Score with the cumulative area from the left to locate it. In the solution from example 6, example 5. All right, let's see what else we got in here. I just want to make sure I give you every information. Where's this example 6? This is example 5, so I don't know where example 6 is. I'm assuming it's below us. So the z-score gives us these cumulative areas. Okay. These are the special cases. 95% is this. This is your 0.05. This is the biggest one. This is your alpha levels that we like. be like a lot. This is for 0.001. This means like you just about have everything. So use the same bone density scores in our examples. So they meet up. Find the bone density score corresponding to the 95th percentile or the top 5th percentile. So how do we words? We can use this table. I'm finding table A-2. Would be in the introduction. That did not help us. Could be in the appendices. Nice. We already got it. So these are the ones I did before, all the binomial ones, which is cool. Here are our z-scores, and this is for positive. So we can work backwards with these to get the z-scores based on the probabilities. And then we have cumulative area to the left and cumulative area to the right. Okay. Below this, and I'm assuming to the right is going to be on the other side. To the right. That's the left. Area from the left. Area from the left. But it's negative and positive. Okay. I'm fine with that. So let's see what ours was. We wanted, let's go to standard, and let's just get this -1. So if you want to work backwards from this table, right? And we know we have 84.1 as we want to be the percentage. Sorry. Here's our 84, 86%. Here's 80, see 8.839 and 0.841. We round it to 3 decimal places. We are between 0.9 and 1. This would be probably here. So 0.9 and 1 for this one. That's how you get the z-score going backwards if you know it's 84%, which is nice. So we'll use the table for these examples. Back. Let's go back. So we want the 95th percentile, right? We want everything 95th percentile with a standard deviation of 1. And let's see what the 95 is going to be. Now, if I go back to the table, sorry, I want it right here so I can go right back. Well, we know it's 95%. Okay, so we know this is going to be a positive value. All right, so let's see where 95% is. All right, so 95%, they say it's right here. Ta-da, they give us this little one. 95% is between, 95% is what? 0.16, between 4 and 5. 0.1645, right in the middle. Ta-da, they gave this little dot for us. Exciting stuff. Let's see if I can do this with the programs to go backwards. So we can use the table to go back and forth. So the table helps us. We can use, they say we can use Excel. It says normal.inv. All right. Find the bone density test score that separates the bottom 2.5% and find the score that separates the top 2.5%. So to figure this out, we want between 2.5% and 2.5%. So we can look at those values. So the bottom 2.5% and the top 2.5%. So I'm going to see what it says, but then I'll probably just do it with Excel, right? It's going to say it's 1.96. So 2.5% is 0.025. So let's see if we could actually, they're telling us not to do stack crunching with Excel. Is there a way to go backwards with this if I go to calculators? Nope, this is all they give us. Maybe if I go into options, they'll give us some more things. No. Okay, so we can't use this one to solve it. But guess what? That's why we have Excel. That's why we've got other things we can use for this stuff. So I'd probably just use the table because I've always used the table, but I might as well see what Excel has for us. I'm gonna open it on the app version. I probably would use the actual table every time for this one, but let's see. It says normal.inv equals normal. Oh, yeah. Oh, sorry. So it's norm.inv. So this is the inverse of the normal function. We can just use the web version. This is probably the one you're looking at anyway. So here we go. Normal.inv. All right. So basically, this is what we need. Let's first, before we, so this one's the 95th percentile, right? This is the one we did before. So let's go. The first thing we want to use the probability, 95th percentile. And then our mean, in our case, is 0, and our standard deviation is 1. And it should spit out this 1.645. Nice. And it does. How beautiful is that? We got it. So that was really easy, actually. So let's do this one with the 2.5%. So let's do it. So equals norm. Oh, God. Sorry about that. Just looking at too many things at once. Equals norm dot inv. And now we need basically 0.025 0, comma 1. Now we need the same thing for the other side, equals norm dot inv. Let's do the normal dot distribute one thing at a time, nv. And now it's going to be negative 0.025 0, 1. This just means the number's too long, so you just got to extend it, unless I messed it up. 0.02501. I guess we can only go positive for this. Yeah, so we can only go positive for this, and then we have to change the values. We would just have to change the sign because it's symmetric on both sides. Let's see what happens when I just do the normal dot distribution. All right, so let's do one of the ones we did before. So they like using the stack crunch because it gives you the picture for this. The first one we did was what is it at, well, one of the ones we did was area to the right of -1. What was the very first one we did? Everything to the left of 1.27. Let's see what we get. So x is the value. So our first value is 1.27. That's our x. Our mean is 0. Our standard deviation is 1. And then I guess I'm going to put true. Oh, because one's between and one's not. 0.8975. 0.8975. Wow. So you can use Excel. That's fun. I like the StatCrunch better. I guess going backwards for the inverse of the normal, Excel will do it. What would I be doing? I'd probably be using StatCrunch and then I'd be using the table. That's what I'd be doing to go backwards. Let's see what else we got in here. All right. We did this one, the 1.6 and the negative 1.6. All right, so for the standard normal distribution, a critical value is a z-score on the borderline, separating significantly high and significantly low. This is that 0.05 that we're talking about. This is the 0.25 that we're talking about, the 2.5%, which basically means, ready? Because if I have 2.5% on one side, 2.5% on the other side, that equals my 5%. So that's my critical values. That's what it means. So that means they're very high or very low. So find the value of the z of 0.025 and let alpha be 0.025 in the expression. So the notation of z-score is 0.025 is used to represent a z-score with 0.025 to its right. All right, so we know it's 1.96. Okay, 0.0975. Question: when finding the z-value of a particular, area, of a particular alpha, note the area to the right, is the area to the right of it, gives some technologies give cumulative errors to the left. To find this, to resolve this, we do 1 minus a. So for example, all right, so they're letting you know that if we want to the other side, to the right, because all everything we're doing is to the left. If we want the other side to the right, we have to do 1 minus alpha to get the other value. So for StatCrunch calculators, we go to normal, calculate by 0 and 1, enter the z-score, middle box known and selected, and click compute. I just showed you on Excel, normal dot distribution, which is fine. Finding the z-score from a known probability, insert function, normal dot inverse. Okay, so these are the two different ways. All that was tough. We might as well look at the problems. So I know this video is getting long, but let's knock it out. Let's see what our problems have in store for us. We've got Excel, we've got a table, we've got StatCrunch. We should be fine. So 1 through 4. Let's get it going. All right. What's wrong with the following statement? Because the digits 0, 1, 2 through 9 are normal results from the lottery drawing, such a randomly selected will have a normal distribution. This doesn't seem right at all. Okay. They shouldn't have a normal distribution. Why not? A normal distribution looks like this, which means more numbers are going to fall in the middle. That means the numbers like 4 and 5 will happen way more than the other numbers. There's certain numbers in the mean that'll be different. So it's not normal. This means we're going to have a what? A uniform distribution where everything is going to be 10%. Why 10%? There's 10 numbers. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Each of them has a 10% shot of it occurring. So if we add all of these up, we get the 100%. Everyone has an equal opportunity. We're not falling into the middle, so it's not a normal distribution. Okay, let's go to number 2. A normal distribution is informally described as a probability that's bell-shaped when graphed. Draw a rough graph of a curve having a bell shape. Oh, okay, well that's pretty simple. We're high in the middle, low here. We know this is going to be 68% of our scores. There's our mean. It's going to be +1 standard deviation, -1 standard deviation. Then we've got this one, which is going to be 95%, which is going to be -2 standard deviations, +2 standard deviations. And we have this one, which is 99%, which is +3 standard deviations, -3 standard deviations. And there we go. All right, number 3. Identify the values of the mean and standard deviation from the normal one. All right, so the mean's always going to be 0, and your standard deviation is going to be 1 and 4. What does Z of A indicate? This is your Z-score of alpha, which basically means the critical values of what we want to find. So here's 1 through 4. Now I got to go 9 through 12. Okay. In exercise 9 through 12, find the area of the shaded region. Okay, so they give you the Z-scores already, which is really nice. So I said I was going to use StatCrunch. We can use the table. Maybe I'll try to use all of them, right? 1 StatCrunch, 1 Excel, 1 table. How does that sound? And you can pick your favorite. So the first one I'm going to do is with, I said I'd do the first one with the StatCruncher. Here's your StatCruncher. We're going to go to Stat Calculators. I'm going to go to Normal. And the first one is 0, 4. We want everything to the left of 0.44. And that's what I'm going to put here. And we got 0.670. They say they want 3 numbers. I'm going to give you 3 numbers, 0.670. That's the first one. All right, the second one, we want to the right. All right, we want to the right. Now, I should have gone the other way because Excel only goes one way. So I have to subtract this from whatever we get from our answer. So we'll use Excel. And hopefully I don't mess this up. So we go equals normal dot distribution. Our x is negative 1.04. Our mean is 0. Our standard deviation is 1, and I'm going to put true. All right, so I got 0.1491. So I'm just going to take this answer and subtract it because right now I have this piece, but I want the other piece. So this is what they mean by the subtraction. So 1 minus the answer, sorry, equals 1 minus the answer. I got 0.851. Let's double check with this one. 0.851. I flip this. We want, sorry, negative 1.04. The reference value must be a number. Our mean is 0. This is 1. We want everything that's going to be greater than negative 1.04. Oh, I keep hitting equal sign instead of minus. Oh man, wow, my eyes are off. Sorry about that. You know, we all make mistakes. 0.851. Sweet. And for this one, we got 0.851. We got the same thing for both. Gotta love it. All right, the last one, I'm going to use the table. Oh, and it's a between. So I have to basically subtract these two. All right, well, I might as well just do it on StatCrunch first and then look at the table. So here we go. So we're going from negative 0.84 to 1.28. So we should get 0.699 as the answer for this one. But let's look at the table. All right, the first one we want is to the left of this one and then to the right of its opposite. So let's look at the table. The left of one, since they're both to the left, I'm going to go to the left of this one, and then I will have to go to the left of the opposite of this one. I know that sounds really confusing, right? Because I have to go opposite, but said I wanted to show you, how about I just show you the table for this one so I'm not getting all crazy. All right, so let's just do the table for the 0.670. So this is 0.44. And we're just going to work with it. All right, so we have to go to table. And the first one was a positive z-score. And we wanted 0.44. So here we go, 0.44, right? 0.44, 0.4, 0.4, and then we got 0.670. That's exactly what we got. Ta-da. The other one I'd have to subtract and find it. So, but that's what the table too. If we want to go the other way, we have to subtract it first to get that 0.851. If we want to go the other way for this guy, it says a negative 0.104. Whatever answer we're going to get, we're just going to have to subtract it by 1. So negative 1.04. So we go to negative z-scores, negative 1.04. Negative 1. So hard to see this. So here's 0.04. I'm in this middle. And here's our negative 1. See, we get 1.492. 0.1492. 1 minus 0.1492. And the exact same thing, 0.851 when you round. All right, so I might as well just show you 12 using the StatCrunch. The StatCrunch for this one's the easiest. That's why you should be good at all of them. But I showed you using the table, which is what I wanted to do. It's just be such a pain to do both of these numbers and then either add them or subtract them together. That's a pain. All right, so here's 12, negative 1.07 to 0.67. Guess the real key is just trying to understand what it means. I think what it means is the most important part. We have 2 minus signs. I'm not going to make that mistake again. Compute. Oh, sorry. This should just be a 0.67. And we have 0.606 for this one. Cool. All right, so I did the first two groups. Here's 25 and 30. Let's see what we got. All right. Assume that a randomly selected subject is given a bone density test. Test scores 0 and 1. In each case, draw a graph, then find the probability of the given bone density. If using technology, go to 4 decimal places. Cool. 25 is between 1.5 and 2.0. So here's my picture. Okay, so we know this is 0. I mean, these are going to be 1 each. So ready? -1, +1, -2, +2. So for number 25, we are between 1.5, right? You're between 1.5 and 2.0. This is it. Ta-da! They want 4 decimals. I'll give them 4 decimals. Point 0.0441. Because you got to round this. 0.0441. Ta-da! This just means it's about 4% of my scores. All right, let's do 30. 30 is between negative 0.77 and 1.42. So this is, sorry, 30 is between negative 0.77, which is right here, and 1.42, which is here. So we want all of this business in the middle. It's going to be 1. It's negative 0.77. Sorry, I'm making mistakes. All right, 0.7015. 0.7015. This means about 70% of our scores. Awesome. All right, now 37 through 40. I'm assuming these we're going to have to go backwards. Assume that randomly bone density test scores are normally distributed with a mean of 0 and standard deviation 1. Draw the graph. Find the bone density score corresponding. So find the 99th percentile. This is the 9th. So this is everything. So this is the this bone density score separates the bottom 99% from the top 1%. So this is almost everybody. Okay. So remember 0, -1, -2, 1, 2. So basically, we're somewhere over here. We don't know what the value is. We just know that this should be around 99%. So because we got to go backwards, I'm going to use Excel for this. Equals normal dot inverse. Our probability is 99%. Our mean is 0. Our standard deviation is 1. What do we get? I didn't make it a percentage. So it has to be a probability. It needs to be a percentage. All right, so this means our z-score is 2.33. They wanted to how many decimal places? 2 decimal places. 2.33 is our answer. That's what this value is, 2.33, which makes sense. All right, let's try this next one. 38. All right, so find the 15th percentile. This is score separating the bottom 15 from the top 85%. So what score? So ready, so 0, -1, -2, 1, 2. All right, so if we are in the bottom 15th percentile, right? We're somewhere over here. I don't know exactly where we are, but we're somewhere over here. So the score separating the bottom 15% from the top 85%. So let's look at it. And if I made a mistake on some of these, feel free to let me know. But this is how I think that they want them done. So equals normal dot inverse. And we want the 15th percentile, which is 0.1501. It's negative 1.04. Negative 1.04. Sweet. I was pretty close. I like it. I will take that all day. Negative 1.04. A little bit more than 1. I was pretty close. All right, 39. Bone density scores in the bottom 1% and the top 1% are used as cutoff points for levels that are too high or too low. Find the readings that are the cutoff values. All right, so I'm going to do this 1%, and then we just know it's going to be opposite on the other side. So that's what I need. So basically for 39, I know it's going to be this, it's going to be this. But because this is like symmetrical, it's like a mirror, whatever I get over here, it's just going to match over here. So that's what I'm going to do. So equals normal dot inverse. And I'm going to do 0.0101. Negative 2.33 and positive 2.33. Those are the two answers. All right, so I'm going to let you do this one. I'll just tell you what the quartiles are. Remember, quartile 1 is what? 25%. Quartile 2 is 50%, or the median. And quartile 3 is what? 75%. So you just do what we did above, but these are your percentages. Find the critical value to 2 decimal places. Well, this 41 is the exact same thing as this one, so I might as well do this one, and then you can do the rest. I did just about everything. So where it says z is 0.25, it just means what is the 25th percentile? So I might as well just do this one. I know that was long. I hope this was useful. I get it was hard. I'm not trying to pretend it's anything different from being hard. All right, so this is 0.6, 2 decimal places, negative 0.67. Did I just lose my thing? It looks like it. The both of these are negative. My God, I already forgot. uh, 0.67. What does that mean? Right here. Boom. There is 25% of the scores. All right. Good luck. This one was really tough. I guess they're all going to get kind of tough, but feel free to reach out to me. If you need help with this one, this one's really challenging, but I'm here to help. And good luck. I did just about everything.